I give you delta binding energy. Delta E, I mean delta binding, equals to the binding energy of one nucleus minus the binding energy of another nucleus. Okay. Here we have a beta plus transition. We have a beta plus decay. Uh, N nitrogen decays to carbon 13. During the transition, we have beta plus emission. Okay, so we have a transition between nitrogen to carbon, and we have beta plus decay. I give you delta binding energy equals to the binding energy of nitrogen minus binding energy of carbon. Okay. Anyway, I calculate the absolute value of delta binding. These two nuclei, we say here, between the mirror nuclei. What I mean by mirror nuclei? Okay, it's important. The question now, find the nuclear radius constant R0. Let me explain, first of all, what I mean by mirror nuclei. If I say here, we have mirror nuclei. For example, first of all, we have two nuclei, X1 and X2. X1 has Z1A1, X2 has Z2A2. We have these two nuclei are mirror when Z1 equals to N2 and Z2 equals to N1. And we will get the same, we get the same mass number, A1 equals to A2. Okay, if I take here the example of nitrogen and carbon, here we have nitrogen 13, 7, where Z equals to 7, N equals to 6, carbon here, Z equals to 6, and N equals to 7. As you see here, Z equals to N, and N equals to Z. In this case, we say that these two nuclei we have a mirror nuclei. Anyway, now I want to find or to calculate the value of the radius constant R0. You know, in general, we have a relation between the binding energy and the radius of the nucleus. You know, the semi-empirical formula of binding energy calculated by the liquid drop model equals to the summation of many terms. One of these terms, a coulomb, is in function of is inversely proportional to R0. This relation is calculated before when we calculated the value of the Coulomb term, and we calculated the value of AC. AC depends on the value of R0. And here I need to calculate or to use the liquid drop model to find delta binding energy. Okay, here you have to know we have the carbon has 6 proton and 7 neutron. The notation will be Zn, and the nitrogen has Z prime and N prime. Okay, Zn are for the carbon, and Z prime and N prime are for the nitrogen. So we can write delta binding energy here by using the semi-empirical formula. You know, binding energy final, you can put delta binding of carbon minus nitrogen or of the nitrogen minus carbon. Anyway, you can write the absolute value of delta binding. You know, the binding energy here equals to the the volume term minus the surface term, Coulomb, symmetric, and pairing. Okay, minus the same term for the nitrogen. Okay, just I write the value of the binding energy of each one. Okay, you know, we have the same A. The mass number of nitrogen equals to the mass number of carbon. So, and we have A is constant. So AVA equals to AVA prime. We have AVA minus AVA prime. So we can cancel this term. Also, here we have A surface, A power 2 over 3 minus plus the same value. We can cancel them. And also we have delta pairing. You know, delta equals to A pairing times A power minus half. So it depends to the value of A, and we have the same value of A for Z and N for nitrogen and carbon, so we can cancel them. Finally, we have this value, this one and this one. We write down uh, these values, okay? We have 4 terms. Look here. Uh, we can take AC divided by A power 1 over 3 as a common factor. Here we get Z square prime minus Z square, okay? And also we can take asymmetric divided by A as a common factor. We get A minus 2Z prime square minus A minus 2Z square, okay? You know here, A minus 2Z prime equals to N minus Z. It's the same because N minus Z equals to, you know, N equals to A minus Z. So we can write A minus Z minus Z. So we get A minus 2Z. Okay? And we have N equals to N equals to Z1, Z2, or Z equals to N2 and N equals to Z2. Okay? If you substitute the values here, you can cancel each other. Okay? Anyway, finally, we simplify the calculation. You know, finally, we get z prime square minus z square. We have z prime equals to 6 and z equals to 7, and here we have absolute value. If you calculate 6 square minus 7 square, we get 13. 13 equals to a. We have a equals to 13. Okay, we can substitute the value here, a divided by a power minus or 1 over 3. We can put this one here and we simplify the relation. We get finally a coulomb times a power 2 over 3. Okay. Anyway. Okay. Now we calculated the value of delta binding energy equals to AC times A power 2 over 3. We can put this one here. We get delta binding energy divided by A power 2 over 3 equals to AC. And we calculated in the last videos the value of AC, which is equal to 3k E square divided by 5R0. Okay, so from this relation, I have the value of delta binding energy equals to 1. I think 1.119. Anyway, it's given. Let me see. Yes, 1.19. And we have the value of A equals to 13. We have the value of K equals to 1 over 4 pi epsilon 0 equals to 9 times 10 power 9. We have the value of E, it must be given, equals to 1.6 times 10 power minus 19. Anyway, you can calculate easily the value of R0, which is equal to 4.01 femtosecond or 4.01 times 10 power minus 15 meter. Okay, this is the value of R0.